Welcome back, team, to another APES Screencast. Today we're going to start Chapter 14 and cover Sections 14.1 and 14.2. Chapter 14 is all about geology and non-renewable minerals. The chapter begins with a discussion of rare earth metals. Rare earth metals are 17 chemical elements that are crucial to today's technologies. They can be found in everything ranging from LCDs, LED light bulbs, fiber optic cables, and cell phones. Without affordable and accessible supplies of rare earth metals, we could not develop the cleaner technologies that are needed now and in the future. In the diagram on the left, you can see all the different rare earth metals found in an iPhone. On this periodic table, you can see all rare earth metals highlighted. This diagram highlights the different rare earth metals that go into the construction of an electric vehicle. Again, it highlights the need for rare earth metals in developing cleaner technologies. This is the Mountain Pass Mine in California's Mojave Desert. It used to be the world's leading producer of rare earth metals. Today, it is the United States' only rare earth metal mine. This is a photo from a rare earths mine in China. Today, China is the world's leading producer of rare earth metals due to lower labor costs, looser environmental standards, and government subsidies. This article from Wired highlights one of the environmental side effects of the rare earths metal mining industry. Hungry miners in the Congo have been hunting gorillas for food. In Section 14.1, we're going to talk about the Earth's major geological processes and mineral resources. Let's start with some geology basics. Geology is the study of the dynamic processes that take place at the Earth's surface and in the Earth's interior. The Earth is made up of three major concentric zones, or layers. The innermost layer is called the core and is made up of a solid inner core and liquid outer core. The second layer is the mantle, and the mantle is made up of a solid inner mantle and semi-solid or partially melted asthenosphere. The outermost layer is the crust, and the crust is made up of the continental crust and the oceanic crust. Because oceans cover about 70% of the Earth's surface, about 71% of the crust is oceanic crust. This diagram shows the structure of the three major layers of the Earth. The prefix litho means rock, and this diagram shows how the solid lithosphere and semi-solid asthenosphere relate to the crust and the mantle. Make sure you know the difference between minerals and rocks. Minerals are naturally occurring compounds that exist as crystalline solids, and rocks are solid combinations of one or more minerals. On the left, you have an example of a mineral, amethyst, and on the right, you have an example of a rock, sandstone. There are three major types of rock. The first is called sedimentary rock, which is rock made up of sediment. Sediments are materials broken down by weathering and erosion. It could be dead plants and animal remains, like in the case of coal shown on the right. Or it can be tiny particles of weathered and eroded rocks, like the sandstone shown on the left. The second type of rock is called igneous rock, and is produced from molten or melted rock. It can either begin underground as magma or above ground as lava. The third type of rock is metamorphic rock. Metamorphosis means changing form, and metamorphic rock forms when existing rock is subjected to high temperatures, pressures, fluids, or some combination of them. This image gives several examples of the three different types of rock: igneous, metamorphic, and sedimentary, and the minerals that comprise them. The Earth's rocks are actually recycled very slowly. The way in which rocks are recycled over millions of years is called the rock cycle. And the rock cycle includes processes like weathering, erosion, melting, and metamorphism. Make sure you understand that weathering is the breaking down of rock, and erosion is the removal and transport of rock by things like wind and water. This diagram shows how weathering is the breaking down of rock and how weathering can occur biologically by living things, chemically through chemical reactions, and physically by things like wind, rain, and ice. This photograph shows how weathering and erosion by wind can create unique rock structures. This is another diagram of the rock cycle, highlighting the processes involved in changing one type of rock into another. The purpose of mining is to collect ore from the ground. Ore is a rock that contains a profitable concentration of some mineral. Ore comes in two forms. There's high-grade ore, which has a high concentration of the desired mineral, and low-grade ore, which has a low concentration of the desired mineral. Metallic mineral resources that we mine for include things like aluminum, iron for steel, and copper. The photo on the left shows an example of a gold ore. Non-metallic mineral resources that we mine for include things like sand, gravel, and limestone. Sand is commonly used in the production of glass, brick, and concrete. A sand mine in India is shown here on the left side, and a limestone mine in Australia is shown on the right side. In section 14.2, we're going to talk about how long non-renewable mineral resources might last. Places around the world where we can find and extract minerals profitably are called reserves. The map on the right shows major uranium reserves in the United States. Uranium is used for nuclear power. The time it takes to extract a certain portion of the minerals in a reserve is called the depletion time. This portion is usually around 80%. Metallic and non-metallic minerals are non-renewable resources. As we continue to extract them from the ground, they become more and more rare. At a certain point, it may no longer be profitable to continue extracting them from the ground. At this point, we say they're economically depleted. When a resource is economically depleted, we have to find other alternatives. Things like recycling, reusing, wasting less, using less, finding a substitute, or doing without. The photo on the left shows aluminum recycling. The photo on the right shows how TV dinners used to come in aluminum trays, but have now been replaced by things like paper and plastic. This graph shows how alternatives like recycling, reusing, and reducing consumption can extend the life of a mineral resource and decrease depletion time. Going back to the case study of rare earth elements, I do need to highlight that rare earth elements actually aren't that rare. Mining rare earth elements, however, is highly labor-intensive and environmentally disruptive. Currently, China produces about 97% of the world's rare earth metals and oxides, and the United States produces virtually none. Subsidies and tax breaks to mining companies keep mineral prices artificially low. This is what happened in China. The Chinese government has been supporting the Chinese rare earth metals industry, and as a result, Chinese rare earth metal prices have been so cheap that other countries just can't compete. On the flip side, scarce investment capital hinders the development of new supplies of mineral resources. Because Chinese rare earth metals have been so cheap, other countries just haven't invested in producing new supplies or sources. When we deplete our supplies of high-grade ore, we can then tap into low-grade ore. There are, however, factors that limit the mining of lower-grade ores. First, it's expensive because of the increased cost of mining and processing larger volumes of ore. Secondly, processing ore requires fresh water, and processing low-grade ore is going to require a lot more water. And finally, because we're mining more rock for less mineral, it will have a greater environmental impact and be more environmentally disruptive. One way we can improve the impact of mining low-grade ore is by improving mining technology. One example of how we are improving mining technology is biomining. Biomining is using microorganisms to extract metals from an ore. This is a slow but efficient process. As mineral supplies on land are depleted, we can look to the oceans. Ocean water actually contains dissolved mineral resources. Unfortunately, these minerals are only present in low concentrations. There are also deposits of minerals in coastal sediments, things like rock, sand, and gravel. The diagram on the screen shows the different minerals and compounds found in ocean water. Hydrothermal vents are hot water vents in the deepest parts of the ocean. They do contain ore deposits that are rich in minerals. There are also metals on the ocean floor. There are things like manganese nodules that are high in mineral content, but are so deep and so spread out that they'd be very expensive to collect. The photo on the left shows a hydrothermal vent, and the photo on the right shows a manganese nodule. This diagram shows a hydrothermal vent ecosystem. The minerals coming from these vents allow bacteria to do chemosynthesis, creating a deep water food web that supports a variety of life.